Good afternoon, everyone. Dr. Alex Wong, Dr. Rosa Chen, Dr. K.L. Chen, and Dr. Wang Cheng, and any other students. I'm a third-year undergraduate student supervised by Dr. Alex Wong, and my project title is Driving Active Electromagnetic Surface with an FPGA. Firstly, I'd like to introduce the uh, concept of matter surface or the intelligent surface and the FPGA. Matter surface is a kind of metamaterial, which is a artificially engineered structure consisting of sub-wavelengths unit cells. If you take a look at the pictures below over there, you will see many squares, small squares on the surface, and the size of each is much smaller than the wavelengths of its operating. They can be used to manipulate the EM waves, like the reflection and refraction and many other interesting effects. And for the FPGA, the full name is Field Programmable Gate Array. This is a kind of digital circuit, but feature as a highly programmable and reconfigurable functionalities. And it is very easily scalable as well, which is a good candidate to control the unit cell of meta surfaces, because for an active device, we need to tune a bit both in real time or by reprogram the surface. By tuning a meta surface properly by using FPGA or other microcontroller, we can achieve desired boundary conditions, and then we can achieve many interesting properties, which is found in the nature. The first example is on the bottom left, which is named negative reflection. You will see in the nature that the light will be refracted. Sorry, yeah, the light will be, oh, I'm sorry, here should be negative refraction. In the nature, the light will be refracted towards the other side of normal line of intersurface between two materials. But by using metal surface or metal material, one can bend the light to the same side on the to the normal line, so you can see the light turn to another direction, which is quite you cannot find this kind of effect in the nature. And the other example I gave here is a work of my supervisor, Dr. Alex Wong. You will see it's called EM cloaking, which means you can place an object in the center area and it will be cloaked or it will be shielded. So it will not be seen by the outer detectors in the operating frequency. And in this project, we design and experimentally demonstrate a meta surface that receives an incident wave and reflect it with adding an orbital angular momentum, which is OAM. So as the pictures illustrates here, the incident wave have a thinner phase front or wave front, which is in the nature, sometimes you will have a spherical wave, so which means the wavefront is a surface of a sphere, but the reflection wave carries a helical wavefront, as you will see in the pictures here. It have a spiral pattern at a cross section and have a helical wavefront. If you take a look. To achieve such a properties, we need to generate a series of desired voltage to be fed to it. When we go to time varying case, a series of voltage wave, Vt, are necessary. AWG means arbitrary wave generator can be used to generate them, as shown in the bottom right. You can see it's a very huge device. So because we have many unit cells on the metal surface, so when the number of cells become large and we need to control them separately, which means the number of channels become large, AWG can be very expensive, and the setup can be very complicated. So this gives us a motivation to develop a new circuit to generate a voltage bias. And on the bottom left, the picture shows an example of voltage wave we need. In this case, we use DAC, which is a digital to analog converter, which is very common in electrical engineering. DACs are usually an IC, an integrated circuits, or the small chip. They can be integrated on the circuit boards and are very easily to be scalable. You can use a set of them for many numbers. And FPGAs is a very good choice to control this kind of ICs when the numbers and then become large. And the FPGA itself is also programmable and the functionality is very flexible. So in my project, what I did is to design and build a circuit, which consists of an FPGA and 4 boards carrying 4 FPGAs on each. So we totally have 60 channels, which can generate voltage in the 100 kilosamples per second, which is a very fast speed. And the voltage range can be from 0 to 10 volts, and the precision up to 1.25 millivolts, which means it's very precise. The pictures below shows a simple setup of circuits, and some cables are not shown here. On the left is the FPGA board, and the right is the DAC board. And here is a photo of the experiment where we are testing the devices. And on the top right, you will see the comparison between the theoretical voltage wave and the experimental measured pace. They are reverted in terms of time because of the need of experiments, but you can see the waveform is very well reserved. They are very close to each other, and the desired sampling frequency can be achieved. And another feature of this project is using the FPGA, which is a very flexible device. The FPGA enables system to be controlled very flexibly in real time without restarting. You can change the functionality whenever you need, like modifying the voltage sequence, adjusting the sampling speed, which means you change the modulating frequency of your surface in wireless communications. And the code of FPGA in the Xilinx, which is a vendor of FPGAs, enables us to develop the program in the high level by using C language instead of just the hardware description language. And by using such a system, we implement the objective of our project. On the left, you can see here is a experimental scanning result of our OAM. On the top is the amplitude. You will see a very dark area at the center, which is called the singularity center. And on the bottom, you will see the simulation and measurement results of phase. You will see a very obvious spiral pattern of phase. It turns around again and again and towards the outer side. And you also can see that the simulation results and the experimental results are very close to each other. And on the right is a setup photo of our experiment. The probe here can move and scan over the area we need to sample the field data. And we also implement a time varying case to generate OAM. So you can see at time of 0, we have no OAM. It's a very regular spherical wave. And when time becomes some time, it have a single spiral pattern. You will see a single tilt here. And sometimes later, you will see double tilts, which is a second order OAM. We can change this pattern very quickly towards the kilohertz, which can be used in wireless communications and other interesting physical applications like the particle manipulation, like the optical tweezers.
Please try to wrap up in 1 minute.
Okay, it's last page. All right. So in the future, we aim to make the surface can change the direction of reflection of wave, such that we can reflect the different harmonics or different OAM towards different directions, which can be called the space-time modulation, space-time multiplexing. This is our next step, and we have a theoretical design here. Okay, at last, I'd like to acknowledge my supervisor, Dr. Alex Wong, for his very kind and helpful guidance, and also Mr. He Hobo, who has graduated from CityU as a former cooperator of this project, and many other members in our group to give useful suggestions, as well as the lab staff technicians for their help during the experiment, and finally, the department to give such a good opportunity on the DURF scheme. Okay, thanks. That's my presentation.